Okay, good afternoon, everyone. Hope you're not too tired after a long day. Is this working? Yes. Okay. Cool. Okay, so who was in the last session in here? Cool. So, okay, so a pretty similar audience. Okay, so in the last session, we kind of saw the kind of introduction to machine learning. What is the idea behind what we're doing? And really the big idea is to say we've got a lot of these different methods, and we're trying to say we have input data, and we want to apply some kind of technique or algorithm or some maths or something that's either going to do classification for us, it's going to take that input and put it into one of a handful of different classes, or it's going to do regression, right? And it's going to give us some number that we can use from it. And we saw in the previous session, we saw some techniques. We saw neural networks, support vector machines, decision trees, and random forests, and things like that. So in this talk, what we're really going to do is we're going to say, well, this is the deep learning Indaba, and what is it about deep learning that is any different to those techniques? Why do we care about deep learning as a thing? Why isn't there a support vector machine in Indaba, for example? And I mean the answer to that question may be fairly arbitrary, actually. But hopefully through this talk, we can see that these deep techniques are providing something that some of the techniques don't have. But that isn't to say that the other techniques are not useful. All of these techniques have their place, and everything really, you should use the best tool for the job when you need it. So what we're really going to look at in this talk is we're going to start off with this idea of machine learning, and we're going to look at kind of the old pipeline. What did we do? How did we do the machine learning? And then how do we move from there into deep learning? Following that, we'll go through probably the standard things that you would think of as an introduction to deep learning. And so we'll talk about neurons and how they relate to logistic regression, which we saw in the previous session as well. How do you train the neurons? How do you stick the neurons together to learn things? And what about all of that makes it deep learning? Why is that even a thing? Okay. We will talk about backprop, and we'll go through that in a little bit of detail as well. So how do we train a neural network? That's the backpropagation algorithm. What is the maths level here? Do we have maths 1, 2? A little bit? No? Okay, cool. So that's right. So if we get a little bit lost in the maths, don't worry. Make sure you get the intuition. My feeling always is that the intuition is what matters, and we can always sit down and figure out the maths when we have to program it. Okay. But if you get that intuition, if you get like, okay, backprop just does this thing by going from here to there, and it remembers the mistakes, right, and fixes them. So as long as we can get this kind of intuition, I hope that that's valuable. And then we'll talk about some different types of neural networks and things like that as we go. So I always think that the easiest, the most intuitive idea for machine learning is vision, in my mind. It's something we're very good at. So we want to say, okay, cool, we want to recognize all our handwritten digits. So these are digits from MNIST. And we can see that they're all these digits. And if we were to write an algorithm to recognize these digits without machine learning, what would we do? Like, it's not an overly straightforward thing. You know, we might go in and say, okay, well, ones are kind of a straight line, so maybe we can have a for loop that runs down a column and looks for, there's nothing that's obvious here, right? And so sometimes the problem is that we'll need to write and specify an algorithm exactly. So there we have to give it in a lot of detail, right? And so doing that can be really hard sometimes. And so the idea of machine learning is then to say, well, can we get the computer to figure out these steps by itself, right? And fundamentally, when we're doing that, is we're saying we're doing some classification or regression type problem, and we've got a model, and learning involves fitting the parameters of those models. So if we're doing linear regression, then we're trying to say, we want to take a straight line and put it on somewhere, and kind of what should the best parameters of that straight line be, right? Fundamentally, machine learning is that, right? Sometimes we have straight lines, sometimes we have complicated billion parameter functions, right? But fundamentally, we're doing the same thing. We're fitting the line, and we're trying to say what should the parameters be so that that line fits things best, or classifies things best, or predicts some number best. All right. So we kind of head into this idea. Now we need to say we want the machine to learn. We want it to figure something out. So what exactly is that? Do we have some kind of more formal mathematical definition of what learning is? And really the idea is to say that when we learn something, we have experience. I put my hand on a stove and I get burnt, right? I've got some data, right? And then from there, the task now is making tea or cooking dinner or something, right? And so now I'm saying I've got some experience. Putting my hand on the stove was not a good way of cooking dinner, right? And so we can kind of say we have a performance metric that says good or bad. We've got experience that tells us what happened when we did some task, right? And then hopefully as we go, the learning process basically allows us to say that over time, our performance increases as we get more and more and more experience, right? And so really the things that we care about is we want to say, what problem are we trying to solve, right? We've got some problem or some task, T, right? We've got some experience, and in this case, in machine learning, it's generally data, right? So we've got our data, and then we need some kind of performance measure that says, are we doing a good job or not, right? And preferably we want a performance measure that's giving us back useful information often, right? And it becomes very difficult if it's very difficult to evaluate that performance measure or things like that. But ultimately, if I have lots of pictures and I want to classify them as 0 to 10, then what we want to say is it must be related to the error in some way, right? And there are lots of ways that we can specify this performance measure, but we don't need to worry too much, as long as we have some sensible performance measure. All right. So then the overall machine learning process then kind of has these different aspects to them. We start off and we say we have our data, right? From our data, we need to find some sensible way to represent this so that the machine learning system can do something with it, right? And generally when we say we're doing that, we're talking about features. And so we're trying to say, if I've got a neural network, we have inputs that are an input to each neuron. If I have a decision tree, I have a whole bunch of data that are maybe all different categories, and we're applying different questions to each of those categories. If I've got a support vector machine, those must all be numbers that we can throw into the formula, right? And so we need to represent our data in a way that is sensible that the machine learning algorithm can understand, right? And that's what we mean when we say features, okay? So if we go back to our image example and we say I have an image of a 0, right? What are the features, right? That's maybe not an obvious answer, but we could just say, well, let's take the image and unroll it into one super long vector, and the vector is just all the pixel values as we go, and then that's great. But maybe we could have a more useful feature. We could have a feature that says, is there a presence of a loop, right? Or how many of the pixels are dark and how many are light, right? And so we can get quite creative with the features, actually. And if we can come up with sensible features, that can make a really big difference. Okay, so we'll look at that a little bit as well. So we've got feature extraction, we then do the learning. And the learning says we have some complicated model. It's a support vector machine. It's a deep neural network. It's a whatever, right? We have our model, and it has parameters, and we now need to pick the values of all those parameters in a way that maximizes our performance metric, right? So we pick the parameters that make us the best at cooking dinner, right? Or at classifying digits, or dogs and cats, or whatever. And then after that, we do something that we hopefully take our machine learning system and deploy it somewhere and do something useful with it, right? And they're hopefully talking about that in the industry track. Okay. So if this is our process, we take our input, we do our feature extraction, we throw it at some method that will do the classification or regression or whatever it is, and it will give us the output. And so if we go to vision, we can say, how can we craft these features in a way that best represents what we're trying to extract from the data? So the presence of a loop when classifying digits is a really useful feature. We hope that we can somehow extract that feature from the pixel data. That can be quite difficult, right? But once we've got those features, we can do that. And so we spend a lot of time designing really, really good features. Because if you have good features, then learning is easy. So for example, if we have this idea where we've got points like this, right? If we take the graph on your left, right? If I try and put a straight line through there, it's impossible for me to separate the blue and the red dots, right? It cannot be done, right? And turns out that an awful lot of machine learning algorithms are just fancy ways of separating dots with a straight line, okay? Including neurons, perceptrons, support vector machines, right? All the fancy ones, right? So it turns out we really want to be able to put a straight line between dots, right? And so we want to have different representations. And so the representation on the left is saying we can't put a straight line there, and so one class of methods is not going to work, right? But if we can extract a different type of feature, right? So for example, if we took that little green cross in the middle and said the distance from the green cross is now the feature, right? Then suddenly all the things that are kind of inside that black circle are smaller than some distance away, and everything outside the black circle is bigger than some distance away. And now in a sense, we've got a nice feature that gives us a way of linearly separating our data, right? But in order to do this, we had to know our data really well. We had to be able to look at it, and we can do that if it's 2D data, right? But actually, that's a really hard thing to do with high-dimensional data, right? It's a very difficult problem to solve. And so overall, this feature extraction, feature engineering problem is very difficult. And so we spent a lot of time over the years, for example, in vision, coming up with different features. And so we have surf and sift and histogram of oriented gradient and interest points and Harris corner detectors and local binary patterns and bag of words and textons and PCA and SVD and 1,000 other things, right? And a lot of these are very good. Don't get me wrong, a lot of these are very good features, and people spent a lot of time coming up with them, and they solved a lot of vision problems for a long time, right? Because people really sat down and said, what are the important aspects of an image that humans look at? So we look at things like texture, right? And if we care about texture, then let's come up with a feature that captures texture, right? And that's what a local binary pattern does. Or maybe we care about gradients, right? We say, when we're looking at the wall over there, there's no interesting texture, and we throw that away, but we do see these kind of big striking window lines, right? And so that's the bit we focus on. So then maybe we care about those gradients, and so we get histograms of oriented gradients. And then and all these other features are useful for something. But it requires that people understood the problems very well. They understood the data very well before they could go into the machine learning problem. All right. And so so let's look at the machine learning problem, kind of if we take logistic regression, which is kind of one of the basic ones, and what we do is we take in some data here, so we've got x, and we multiply it by some weights, right? So we've got just some linear combination of all the weights. We add in some extra term, and then we chuck that through a sigmoid, and that gives us logistic regression. Okay, fairly easy. And the logistic regression, that's going to give us a number between 0 and 1. And so kind of the straight line kind of says, well, we can see where the yellow, green bit there is. That's kind of saying that's kind of the orientation of the line. And things that are on the one side of the line get category 1, and things that are on the other side get category 0. Right? And so we're still just fitting a straight line. Right? We're not really doing anything fancy, right? So if we're doing this, we now need to say, okay, cool, we're pulling out our texture or gradient features, feeding them into this, and then this is going to give us a 1 or a 0, depending on whether it thinks there's a loop or not, or depending on whether it thinks it's a 9 or not, right? And it allows us to do this binary classification. But it really matters what we're doing with the features, right? Features, 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 okay? And it turns out building good features is hard, and it's painful, and it's soul-destroying, and it doesn't always work, and it'll work for one set of images and not another, and now you use a different type of camera, and it breaks everything, and life is just generally hard, right? And so feature extraction is a pain. And if we can avoid it, let's avoid it. All right. And so I would say that that's one of the kind of fundamental principles of deep learning, right? That deep learning is saying the machine learning algorithm doesn't work on handcrafted features we've extracted already, right? The machine learning algorithm generally runs on your raw data, right? And so, sure, we can do pre-processing, and if we know there's something useful, we can extract it and give it to the machine, and that's fine. But the idea here really is that it's the machine learning algorithm's job to learn good features for itself, right? We don't need to be able to do that beforehand. And that's what's really, really nice about deep learning, and what's really giving us these huge leaps in performance that we're seeing in so many different areas as a result of it. Okay. So really the thing here is this idea that it introduces representations that it figures out itself, right? And then from there, it's saying, rather than saying, can we recognize a loop, which is maybe a fairly complex thing to do, we can say, take a step back and say, can we recognize edges, right? And then if we can recognize edges on one level, then we can say, well, we know that when edges cross each other, they're corners. So now we can recognize corners. And then in the next level, we can say, well, we know that when we've got corners like that and that and that with certain edges in between, then we see some kind of curve, right? And so you can almost build up this hierarchical layered system of really easy to extract features into progressively more and more and more abstract features. And so the general idea is that we say your early layers are extracting these kind of raw, low-level features, and as you go further and further and further, you're getting progressively more and more and more abstract. So you go from corners and edges into curves, into ears and tails, into dogs, right? And so you don't have to learn dog or cat at once. You can learn them progressively as you go, all right? And so the idea of deep learning is now that we're merging feature extraction and classification or regression or whatever the problem is. Right? Feature extraction is now part of the learning process. All right. So I've now lost it. Carried it with me for like 2 days and now I lose it. So this is a really, really, really good book called Deep Learning. So this is a photo from one of these. I'm afraid I didn't have access to a scanner. But this was written by Ian Goodfellow, Yoshua Bengio, and Aaron Corville, who are some of the founders of deep learning. So this is really, really good. And this one diagram that they give, I think, captures it really well in a sense of the history of machine learning as well. That we kind of started off with these rule-based systems, right? We had input, we'd hand-designed some specific thing that says, when you have this input, then it's this, and it's a dog, right? And everything was handwritten and hard-coded, right? And that's where we started, and we had rule-based systems. And then from then, we kind of moved into more classical machine learning, and we went input, and then we had all our painfully developed, handcrafted features. And then from there, we'd have some mapping between features and output, right? And that's where we would do our machine learning. And then the next step, we kind of fall into this greater idea of representation learning, where we're trying to say, we don't want handcrafted features anymore, right? We want the system to learn it by itself, okay? And so now we move into representation learning, and it's saying, okay, first learn the features, then learn the mapping from the features to the output, and then that's hopefully the better way of doing it. And then we move into deep learning, which is now saying, can we have this kind of multi-layered approach to learning features? You don't have to learn all the features at once. You can learn the easy ones first, and then group the easy ones to build the hard ones, and eventually you get something progressively more abstract and more difficult to explain. All right. And that's really where deep learning kind of sits, and that's the main idea of it, at this stage at least. Okay. So we have this idea, so we say, okay, we take our pixels, we no longer have to do anything fancy. The system might look at edges, it might take the edges and then build up contours, it might take the contours and build up paws and eyes and ears and fur and tails and whatever, and then give us a dog. So to summarize, okay, these models are giving us better flexibility and power, right? And what they're doing is representing the world as a nested hierarchy of concepts, with each concept defined in relation to simpler concepts, with more abstract representations being computed on top of other abstract concepts. Are we happy with that? Cool. So that's also from the book. Definitely recommend it. It's a very good one. Okay, so we know what deep learning is. How do we make it happen, right? So we often think of deep learning in terms of artificial neural networks, right? We think of them as these really deep networks with lots and lots of layers, and in many cases it is. But I think we maybe need to be careful that artificial neural networks are like, you could have other ways of doing deep learning, right? We've just said now the important thing is this idea of hierarchically learning concepts, pulling features out themselves, all of that stuff. Okay. But having said that, neural networks are probably the one you're going to see always. Okay. Cool. So do we know what neural networks are? Do we know how they work? Yes, no, maybe a little bit. Okay. We will hopefully figure out how they work in the next few hours. Okay. So we start off with a neuron, right? And this is the McCulloch and Pitts neuron, described in the 40s, and it's as simple as it gets, right? We take our input, so we've got x, and x will have a whole bunch of numbers with it. We will take each number and multiply it by a weight. We take all of those and add them up together, right? And then from there, we've got some linear combination of all the inputs. And we then go into the next step, and we say, the neuron will either fire or it won't. If that linear combination of all the features is above some number theta, then it fires. If it's not, it doesn't. Easy. Deep learning waxed. We can do this. So we have inputs, we have weights, we have an activation function. The activation function is what says we either give out a 0 if it's below a threshold, or we give it a 1 if it's above a threshold. Okay? And we can generally write this as some activation function. We've got the linear combination of our weights and our input, and then we've got this extra kind of bias term that we end up adding on. And so the reason that we get this term, so over here we said that there is an explicit threshold theta, right? But that's clunky and it's hard to work with and all of that. So what we can actually do, right, is we can build that in as just another weight, right? So every time we take a set of inputs, we add a 1 to it at the very beginning, right? We just add this 1. We'll call it x naught, right? So we've added that 1, and we've now learned another weight, and we're setting it to negative theta. And now when we learn w naught, right, we're just learning another parameter. We're learning another weight, just like we were with everything else. And now we can say if the value is above 0, it fires, and if it's below 0, it doesn't. So it's kind of centered that activation function at 0, and then the bias has just been added in somewhere else into the math so that we don't need to care about it and forget about it completely. Are we happy? Cool. So we now have a model of a neuron, right, which is entirely different to logistic regression in that we've called it a neuron and not logistic regression. Okay? A neuron is doing logistic regression, right? If our activation function is a sigmoid, rather than that kind of hard cutoff, if it's a sigmoid, it's simply logistic regression in a neuron, right? And the neuron is just a nice encapsulation that we have of it. Okay, cool. So when we then want to do learning, it's now a case of saying we have all these weights, all these weight values and the bias inside each neuron. We now need to figure out those values for every neuron in our system to minimize the number of errors, or in some sense to maximize our performance, right? And that's the part that we've called learning, right? And so we do this learning by applying a process called gradient descent, and in general we use something called stochastic gradient descent. But the basic idea of it is to say, here is a surface that represents our errors, right? And so on this axis going up, it's j, which generally means our loss function, right? And loss is related to our errors. So if we have lots of errors, we've got a very high loss function, and so we want a very low loss function to try and minimize our errors, right? And so gradient descent says we've got the surface, we start off over there, and we take some step in the direction that makes our errors slightly smaller, right? And then from there, we take another step and another step and another step. And we keep going until we find some minimum value of all our errors. All right. And so just inherent with that, we have this idea of the space that is built up where every axis is one of the weights in our system. Right? And so we take a step in that space. It just means changing a weight in some way that makes our error slightly smaller. Right? We take a step in the descent direction. All right. And so we can take big steps and we can take little steps. Right? And so if I'm over here and I say, at this exact position, going in that direction will go down. Right? I can take a little step and I'll go down. And I'll say, okay, cool, now I can do it again. And I can say, which direction is down? And I take a little step. And I take a little step and a little step and a little step. And 4 years later, I might be over there. Right? We don't want to take steps that are too small. On the flip side, we don't want to take steps that are too big. Right? Because if I'm over here, I'm saying, cool, I do want to take a step in that direction. Right? But if I take a step that's too big, I simply end up on the other side of the valley in this case, right? So you kind of have this idea where you want to take steps that are big enough to make a difference, but not so big that you just end up jumping around randomly. Okay. And so we'll see that pops up a little bit later, where you want to maybe start off with a learning rate, a step size that is relatively big to kind of explore a bit. And then as you start finding a good set of parameters, you make your step size smaller and smaller and smaller, so that as you get closer to a good solution, you don't overshoot it. Okay. Cool. So we want to say now, how do we actually update a neuron? Right? So this is the general update rule that we would have for a neuron. So we would say we have some learning rate alpha, right? And that just says how big is our step size, right? And we say we have a target. So we said that our neuron is going to fire or it's not going to fire. It's going to give us a 1 or a 0, right? So we have the target of what we wanted, and then we have the actual output that it gave us, right? So if we look at the first line and the last line, right, we can see if our target was 0 and we predicted a 0, then we were correct, right? We actually don't want to change anything, right? Likewise, if the target is 1 and we predicted 1, we don't want to change anything. Okay, so in those cases, we do nothing. In the other case, do we agree that that kind of target minus the actual predicted value, it's either going to be 1 minus 0, or it's going to be 0 minus 1, right? So that's when we get a value inside the bracket, okay? So we get the minus 1 and the 1. And then in a sense, if the target says, so the target was a 0, we predicted a 1. It means that when we added up all the weights multiplied by the input, that number was too big because we fired and we shouldn't have, right? So then we want to make all of the weights slightly smaller, or all the weights that were involved slightly smaller. Agreed? And on the flip side, if it didn't fire and it should have, then all the weights times the input was too small. And so we want to make all those weights slightly bigger, right? And so that gives us an idea of the direction that we need to move the weights, right? And so in one sense, we're saying make all the weights slightly bigger. In the other one, we're saying make all the weights slightly smaller. Sorry, and I see the slide hasn't rendered properly. That was literally just a dot. Okay, so it was just multiplication. So we're saying, and that should have been an alpha. So our learning rate times by whether there was actually input there, right? If the input was 0, then that weight didn't affect it, and so we shouldn't change the weight anyway. All right. So we can now update a neuron, right? If our weights are too big, then we make those weights smaller. If our weights are too small, we make those weights bigger, right? And it's all about that make them bigger, make them smaller direction, okay? And that's our descent direction. It gives us fewer errors. In the count of errors, we're taking a step into fewer directions, fewer errors. Right. Cool. What have I done? Cool. So then we have a perceptron. Have we heard of a perceptron before? Right? A perceptron is now just a whole bunch of those neurons next to each other. That's it. Done. Okay? So we've now said, okay, cool, we have some kind of image. So in this case, we've got this digit of the 8, right? And we take it and we just unroll it into one long, long vector that's 28 by 28 pixels, 784 pixels, right? One long vector of pixel values. And then those go in. And then we've got 10 neurons all next to each other that are going to give us some value. They're going to fire, they're going to give us a 1, or they're not. And then we would train it so that we hope that the 0 fires when we get zeros, and the 1 fires when we get 1s, and all of those, and they would nice and neatly only recognize their own digit. Okay. So that's what we want. So we've got lots of neurons together. Each of these neurons is effectively doing logistic regression, right? Overall, what it's going to do is it's going to learn a hyperplane, right? So an n-dimensional straight line, right? So we're still just fitting a straight line. And we're saying that things above the straight line, we're going to get 1s. Things below the straight line, we're going to get 0s. Okay. So we're still just doing that, which means that this only really works if our data is linearly separable, if it is possible to draw a straight line between the blue dots and the red dots. Okay. So that's one thing to think about, and so this idea of linear separability is important. And it's why we later on need to have lots of layers all with nonlinear functions in between so that we can build up things that are more complicated. All right. But another problem here is that these neurons are all independent of each other. Do you agree that it would be totally possible for 0 and 2 both to fire in this case? We don't have one neuron suppressing another one, right? So we can add on something called softmax, and what softmax basically does is it sums up all of those outputs, and then we scale it all so that the sum of all of them is 1, right? And it's a nonlinear scaling, but it's not complicated. Cool. So we can now say that we can take something where previously it wasn't going to be nice and linearly separable, right? But we can see that if we can fit one line, it can't correctly classify the data. But then we can fit another line that also can't correctly classify the data, and another line, and another line, and another line. And we can draw all these lines, but eventually if we were to look at all of them together, we could see that we could correctly classify data, right? And so what we can do is we can take this combination of all of these different linear classifiers, and by plugging them all together, in a sense, if we can say this one, and this one, and this one, and not that one, right? Then that could mean something, and that could mean something very useful. So it would be nice if we could do some and or not type of logic with these things, and it turns out that we can. Okay. So let's have a look. So if we want to do Boolean not, right? So not just means we take in false and we give you true, right? Or we take in true and we give you false. We just do the opposite, right? And so we could build neurons with these weights. So we've got our bias where we've just added on a 1, right? And then we've got a weight for it. And then we've got some input. And if that's a 0, then our number that's calculated here will be 10, right? 10 is greater than 0, so the neuron would fire. So if I give it a 0, it gives me a 1. If I give it a 1, then it's going to be 10 minus 20, so it's going to be minus 10, which is less than 0, and so the neuron's not going to fire. So I give it a 1, it gives me a 0. Cool, we can do Boolean not, right? Turns out we can do Boolean and as well, right? And so we now have 2 inputs, right? And we can see, in a sense, it's still this idea of linearly separable, right? So we can stick a line, and if it's on that side of the line, it's true, and if it's on the bottom of the line, then it's false, all right? So 0 and 0 is 0, 0 and 1 is 0, 0. Okay, we know how that works. True and true is true, right? So we only get true when it's both of them. And so if we look at those numbers, we can plug in some numbers. If we go 0 and 0, we get minus 30. Minus 30 is less than 0, so it gives us a 0, right? If we have 1 and 1, it's going to be minus 30 plus 20 plus 20. So it's going to give us 10 greater than 0. The neuron fires. Okay. Are we suitably convinced that we can do AND? Right? Same with OR. Right? So OR just means at least one of them. So we start with negative 10, and then if we either get a plus 20 from the one or a plus 20 from the other, or plus 20 from both, either way, we're above 0 and the neuron fires. So we can do this kind of thing, and in every case, there was basically the straight line that we could draw, and it was true on one side of the line and false on the other side of the line. Unfortunately, there are some logical operations that you can't do with a single neuron, right? And so take not XOR, right? So XOR just means one and only one of them is true, right? So you can have tea or coffee, but not both, right? And you can't learn XOR with a single neuron, right? But what we can do is we can plug a few of them together, right? So we can do something like this. And we can say, well, exclusive OR is going to be, or not XOR, is going to be right when either they're both off or they're both on. So it's going to be kind of in that first quadrant and in that third quadrant, right? And that's why we can't draw a straight line and say above the line it's one and below the line it's another. But if we add in extra neurons, right, then we can do it, right? Pointer. Cool. So we can now say we know how to do AND already, and so we can see we can build that with the red neuron over here. So x1 and x2, we're in this first quadrant, right? And this neuron will tell us if we're in the first quadrant, right? Then this other quadrant is when both of them are false. So not x1 and not x2, right? And so we can build a neuron that will do that. And then at the end, when we want to say not XOR, it's either the first quadrant or the third quadrant. And so we can have another neuron that ORs the two of them together. And so now what we're doing is we're saying when one neuron isn't powerful enough to learn this by itself, two neurons with another layer on top was. And we can now learn something that's quite a lot more complicated. Okay. And so this is why it's now important that we have these neural networks with multiple layers. And we can see how having multiple layers gives us more and more and more complex, more capacity, right? We can learn more complicated things. Okay, cool. So if we now take some neurons and stick them together. So on the left, we've just got the single neuron by itself, right? What if I were to take two neurons together, right? So we now have this kind of ridge that forms where the two of them agree, and then it falls off where one disagrees with the other, right? And so we can build up a ridge that looks like that using two neurons, right? What if I took multiple ridges and stuck them together, right? Like on the left, I can now make this little peak in the one section, right? Or on the right-hand side, I can make graphs that look like that, right? But what's important is that taking graphs like this and sticking them together and together and together and together allows me to build any function I want. And by combining them in this way, this is why neural networks are called universal approximators. They can a sufficiently complicated neural network can learn any function, any analytical function we give it. All right. And so we need to be careful with that. We need to make sure that we don't learn with neural networks that are so powerful that they just interpolate all our data, right? That's called overfitting, right? We need to watch out for that because neural networks are powerful, they can do that, okay? So this is important. So we can approximate any function. That's what makes neural networks really nice for learning, because we're now saying, well, we don't know the structure of our data. We don't know that we need to learn a quadratic or a cubic or something like that, right? So if we have a complex neural network that can learn whatever function we need it to learn, then that's really useful, right? Because now we're no longer limited to linearly separable data, right? Which we would be if we were just doing logistic regression or a linear SVM, things like that. Okay. Cool, so we stick all our neurons together and we have our activation functions in between. So we have all our weights, we do the linear combination, we then do the sigmoid and that tells us whether we fire or not. We then go through to the next layer and the next layer and the next layer until eventually we get to our output, and our output hopefully has 10 neurons, and those 10 neurons tell us if it's a 0, 1, 2, whatever. Okay. So we get our multi-layer perceptron. So then we have this idea of the activation function. So we've used the sigmoid so far, and the sigmoid's the useful one, right? And it goes from 0 to 1. As x tends to minus infinity, it tends to 0, and as it tends to infinity, it tends to 1, right? And we can kind of adjust the steepness of the graph by changing parameters, and we can adjust the center of the graph by changing that bias number. That allows us to translate it left and right. Okay. So the sigmoid is a useful one. It really captures this idea of the neuron doesn't fire or it does fire. Okay. It also turns out that it's really nice in that its derivative can be calculated from the number itself. So if I've done a forward pass in a network and I've calculated all the sigmoid values going forward, and I now want the derivative because, spoiler alert, backprop needs derivatives, right? So I now want to calculate the derivative. It's really easy for me to do that because I already have the numbers I need. I just stick them in that sigmoid times 1 minus sigmoid function. Right. And so it's very easy to get the derivative out. So there's some properties that we want to capture. We want to capture this idea that the neuron will not fire or it will fire, right? Preferably in some nonlinear way. We also want it to be really easy to calculate derivatives, right? Those are kind of the things that we care about with an activation function. Okay, so sigmoid is really nice for that. We can also use tan h. Right? Hyperbolic tan does pretty much the same thing, and it turns out you can also calculate its derivative in terms of the function value, right? 1 minus tan h. Okay, so that works really nicely. One of the problems, though, is what is the derivative of this function at x equals 485 bazillion? The derivative is going to be like basically 0, right? So now, if I want to take a step in the descent direction, right, if that step is scaled by the derivative, it's going to be a very, very, very little step, right? And so what we get in really deep networks, as you propagate derivatives backwards, you often get something called a vanishing gradient, right? When you have a little number times another little number times another little number times another little number, and eventually your gradient disappears, and so your learning gets stuck. Right? And so we have the vanishing gradient on the one hand, and in really deep networks, you sometimes get an exploding gradient. So people came up with this next activation function that doesn't have that problem. It just says, okay, well, if we're above 0, we'll use x. And if we're below 0, it's just 0. It's nonlinear because linear functions don't have that kind of non-smooth point, right? And so we do still have that nonlinearity being introduced. We have the sense of the neuron fires or it doesn't, right? And now we have a derivative of 1 or a derivative of 0. Okay, and that helps us with some of those gradient problems. And we'll see that ReLU is quite a useful activation function, and it's quite popular at the moment. It shows up in a lot of different networks. You're very likely to come across it. Okay. Cool. So we said that the task of machine learning is to take our experience, right? And with respect to some task, we want to improve performance as we get more and more and more experience, right? And so within machine learning, we're saying as we get more data, or as we have more iterations, or whatever, right? But we need to do something to improve our performance over time, right? And so we want to minimize our errors, really. That's what we're saying. And so we need some kind of function, which we call a loss function, which is related to our error, right? And if you're from an optimization background, then you would call this your objective function, right? The function you're trying to minimize. Okay. And hopefully, as we minimize our loss function, our accuracy will improve. Okay. We don't necessarily have to use our accuracy as our loss function. That often doesn't make sense. But so one of the big things to think about is what is the type of problem we're looking to solve. So if we're trying to do classification, we might use a different loss function to if we're doing regression, right? If we're doing classification, we have a whole bunch of categories, and we want to check whether things are falling in the correct category. If we're doing regression, we maybe have some sense of how far away are we from the correct number, right? if I'm doing facial recognition, right, I might be giving a face to the neural network, and the neural network gives me some numbers, some space of points, and when points are close together, they're the same person, right? And you can build a loss function that encapsulates that idea. It's called a triplet loss. And so you can get really complicated loss functions that allow you to capture different ideas that you might want to force your network to learn, right? But certainly the common ones, if you're just doing kind of classification regression, is that you'll be looking at things like your cross entropy and your mean square error. All right. But you do get some other complicated loss functions, but fundamentally, you minimize your loss function to hopefully improve your accuracy. Okay. Cool. Following that also is the idea of batch training. Ideally, we want to take the network, we want to give it all the data, push everything through, get a sense of our loss, and then say, okay, which weights do we need to update in order to improve our accuracy, right? But if you've got a data set of 400 bazillion images, it probably takes a very long time to do that. And it turns out that you actually don't need to give it all of your data every single time. What you do is you rather give it some small subset of your data called a batch or a mini batch, right? And you give it the smaller batch, and then you calculate the update based on that set of data. And then you go back and you pull out and you give it a different batch, and then a different batch, and a different batch, right? Once you've got a batch size that's sufficiently big, right, you're already going to be pretty much at the correct gradient to make an update. Right? If you add in another 500,000 samples, it's unlikely to change your step by any huge amount. Okay? So larger batch sizes give you a closer approximation to the real step that you should be taking, but they take a lot longer, and going too big doesn't always help that much. Okay? Also, it turns out empirically that you tend to find you're less likely to get stuck in a local minima. So, I mean, you still have no guarantee you'll find a global minima. But if you take the whole thing, you kind of, one batch will say take a step in that direction, and another batch might tell you to take a step in a slightly different direction, right? And so you kind of do a little bit more exploring as well. Okay. So batch training, you don't want too small a batch because then you might not take a good step, but you don't need batches of half your data set. All right. Cool. Have we heard of the Taylor series? Taylor expansion of a function, right? We just take the first derivative and we could add them on like that. And so if we're thinking of f as now the neural network on our data with respect to some parameters, some weights, right? So we've kind of flipped the neural network on its side and said we're thinking of the weights as the input, right? As I make some small change in the weight, what's going to happen to the loss function, right? And so if I can take the derivative and a Taylor series like this, we can kind of say, okay, well, one's going to give us, if the derivative is positive, then we want to take a step in one direction. And if it's negative, we're going to take a step in another direction, in the opposite direction, right? So if uphill is that way, we go that way. If uphill is that way, we go that way, right? That's fundamentally all the slide is really saying, okay? Take a step in the direction that goes down, okay? And we can figure that all out, but ultimately what the maths works out to be is that this kind of learning rate times negative grad of your function, right? So grad is just, it's like multi-dimensional derivative. Okay, so derivative in multivariable calculus, basically, right? And that tells us the descent direction. And so what we do is we take the weights at the current time step, and then we take those weights and we adjust them by this number here, right? Scaled by whatever our learning rate is, so to make smaller or bigger steps. And then that gives us the weight for the next time step, and we give it a new batch, and then we keep iterating until our neural network has learned everything. Cool. Easy. So, as we build on this, I've now put in j. So j is our loss function, right? So we've got our loss function, and kind of theta's our set of parameters, right? And so saying update all the parameters, what does that even mean? What we mean is to update a specific parameter, theta ij, a parameter from node I to node j, right? That weight. How do we update that weight? And so it's that same thing. We take the negative derivative of the loss with respect to that weight. Okay, so we're happy that the descent direction is simply negative derivative, right? That's the direction we want to go. So we did that in the high dimensional case. Now we're just down to one parameter. And we do this for every single parameter. Easy. We can train neural networks. Okay. Cool. So we're updating them. We take the derivative of the loss with respect to the specific weight that we want to update. Okay. We can do that very easily at the very last layer because we've got the loss and we've got the weight and it's done, right? So that very last layer is the easy one, right? But what happens to the weight further down, right? That weight affects these neurons, which affect those neurons, which affect those neurons, which eventually affect all the neurons up at the top, which affect the loss in some way, right? And so that actually stumped researchers for a long time. And when you hear about the various AI winters, right, this was a large contributing factor to one of them, where there were all these promises about neural networks, and then there's a book published called The Perceptron, which showed that there were some of these limitations, and that while they were kind of arguing that you needed these multi-layer networks, we didn't know how to train them. And that caused kind of a lot of problems in the AI community, and things kind of dried up for a while. But ultimately what happened is that we discovered backpropagation, right? And the idea of backpropagation is to say we have an error at the very last layer that is quite easy to work with, right? So then let's assign blame to every neuron in that layer. Then the next set of neurons, right, we then want to reassign blame into that layer, and then into the next layer, and the next layer, and the next layer, right? And so we start off by saying take the very last layer and blame every neuron for some set of the error. Then go to the next layer and take that set of errors. And so if we've got one neuron on our exit layer and a neuron over here, there's a weight between them. And this weight is some proportion of all the weights going into that neuron. And so we can take the error and we can somehow split it up between them. And if we can do that in a sensible way, then we can say, okay, this weight somewhere deeper, somewhere shallower in the network, then affects the loss in some way, and we can know whether to increase it or decrease it, because that's fundamentally the question we want, right? Turns out you can do that using the chain rule from calculus. Okay, so it's the derivative of the loss with respect to this activation neuron, and then the change in this one with respect to something else, with respect to something else, with respect to something else, until we get to the parameter that we actually need. All right. Okay. The maths gets a little bit hairy. I don't know why this is not rendering nicely. So the maths gets a little bit hairier for the next few slides. If you miss something, don't panic, right? Just remember what's important is this idea that we're back propagating the error, right? We're trying to say, of the total error, what is this specific weight responsible for? And should we increase the weight or decrease the weight? All right. So say we've got this neural network over here. It's cool. So we've got this neural network over here. We've got our inputs, and that's great. We then have our weights, and those go to another layer, into another layer, into another layer, right? At each layer, I'm going to break it into two parts. We've got the one that says we've kind of got the activation, right? So in our input layer, it's just the data, right? Then in our next one, we've got that linear combination of things, so all the weights times the data, right? And I'm going to call that the product. And then we're going to take the product and we're going to put that in our activation function, and that's going to be our activation. Right, so the product is this Z, and the activation is the A. Is that all right? Cool. And we're going to see we're going to need those two things separately because chain rule. Okay. And so we start with our data at the front. We propagate forward first, right? So we've got forward propagation, where we calculate all our activations going forward, and we remember them Because when we want derivatives later, remember our activation functions make it easy for us to calculate derivatives. So we remember these numbers. We go forward, we calculate our loss function at the end, and then now we need to start assigning blame back and back and back and back. Okay, and that's back propagation. Right. And so the big thing here is we've got this kind of responsibility for error for every node. Okay, and that's this delta, and we're going to see that we go to the very last layer and we can calculate it easily, and then we go to the next layer and we can calculate it in terms of the last layer and the weights, and then we go to the next layer and we can calculate it in terms of the next weights, and we keep going back and back and back. All right. So we've got this blame, right? So, deep breath. Chain rule, right? We know the chain rule. The derivative of the loss, J, with respect to the parameter in the previous layer, right? So we've got some loss, and I want to know the derivative with respect to this parameter over here, which is not in the last layer. Okay? So that's going to be the derivative of the loss with respect to the activations in the last layer, right? Times the derivative of the activation, okay, loss with respect to the activations in the last layer, right? Times by the derivative of the activation with respect to the product, right? Times by the derivative of the product with respect to the parameter that we care about. Okay, just the chain rule, right? So we haven't gone crazy yet. Okay. So what is the derivative of the product with respect to the parameter? Well, that's an easy one, right? It's just a linear combination, right? So we know that we said, put a little box in front. Okay. So we know we said that that product is going to be the weights times by the previous activation, right? And so we want the derivative with respect to the weight. So it's quite simple. It's just going to be the previous activation, right? The derivative of 4x is just going to be 4, right? Same thing here, right? So the derivative is just the previous layer's activation. Okay, so we've got that one term. We then go to the next term, right? That's just the activation function wrapping around the product, right? And so we said, so that'll depend on what activation function we pick, right? If we pick ReLU, then it will be a 1 or a 0, depending on whether we were above or below 0. If we pick sigmoid or tan H, then we can write it in terms of the actual activation, right? It was the sigmoid times 1 minus sigmoid, or it was the 1 minus tan H squared, right? So that one, we've got that term as well, and it simply depends on whatever the activation function was that we chose. And then the little bit more complicated one, right? The derivative of the loss with respect to the activation functions, right? We're now kind of saying we need to sum over all the nodes in the next layer, right? Because as I change the weight of the current node, my activation is going to change, which is going to change the activations of all the nodes after me, right? So we've got this neuron over here. If this neuron doesn't fire, then that affects all of these ones. If this neuron does fire, it affects all of these ones, right? So its effect on the loss depends on all of these ones after it. Okay, so we've got some sum of all of those, some addition of everything. Okay, and it's a bit of a hairy thing. But what we can see is that one derivative there that we need to calculate for every neuron, right? And that looks, we can give it a name, we'll call it delta, and we're going to call that the blame. And what we see is that it only depends on the neurons close to the end of the network, right? And the ones at the end of the network are the ones that are easy to calculate. So we start off with that top layer, right? And we get the blame for that one. No chain rule required. We get it for free. Then we can do the other one, and we can get the blame for that one. And now that we've got the blame for those two, we can take a step back and get the blame for this one. And now that we've got that one, we can go back and back and back, and we can propagate this blame from the top of the network to the bottom. Are we happy with that? Okay, so that's back propagation. That's the idea, right? We're simply propagating that error backwards. We're saying, how much blame can we assign to a weight? And once we've got that, we can calculate all the derivatives we need so that we know whether to take a step up or down. All right. Cool. Okay, so we had our ANNs, so we can now say, as we start training, what happens? So we'll have some loss function, and we can see the loss function coming down here. And as the loss function comes down, we can see how the accuracy is going up there. Right? And so this is training some deep network to recognize those same digits we had before. Right? As we keep going, we now say, okay, maybe we can change the activation functions. Now we change from sigmoid activations to ReLU activations. Right? And we no longer have this kind of gradient problem. Right? And so we can now see as our loss goes down, we can see our training accuracy going up still. Right? We can see that our accuracy is very noisy. Right? And so we're kind of jumping around on the loss surface. It means our steps are too big. Right? So we've got that learning rate parameter. We can say take smaller steps. Right? As we take smaller steps, we can see it's less noisy. Right? We can see that so we start with a bigger learning rate, and as we do more and more and more training steps, we progressively make our learning rate smaller. Okay. We notice, in fact, I think, yeah. So we notice over here that what happens is the blue line represents the training set. And we see the loss goes down and down and down, and the accuracy goes up and up and up. We see that the loss on the test set starts going down and then starts going up. Can we see that on the right graph? But its accuracy kind of flatlines a bit, right? When the test accuracy starts going up again, that usually means that we're overfitting. Okay, and so you would need to either stop training at that point, because as you overfit, your network's going to stop generalizing well, right? Because it's training really well on the data it's seen, but it's doing badly on the data it hasn't seen. Okay. So you don't want to break your generalization, but really what you want to do when you start to see this trend in overfitting is you want to implement some kind of regularizer, right? And so overfitting is when we say, well, we've got some green dots over here. We could make the graph loop around and keep those green dots on the right side of it, but it probably won't be learning the trend. It'll just be overfitting the data, right? So we want to regularize in some way, and so there are different methods to do that. Common ones are dropout and L2 regularization and things like that. But overall, what regularization is trying to do is it's trying to stop this overfitting, right? And so you can see in this graph, once the dropout was added in as a regularization, rather than that loss function continuing to go up, we can see it also flattened out once the network kind of got stuck with learning, right? And so kind of they say, all the party tricks are thrown in here, and we can see that we're getting good results. So some of all of these party tricks to think about: what is the type of problem I'm doing? What kind of loss function am I doing? What types of activation functions am I using? Am I adjusting my learning rate as I go? Is it too big? Is it too small? Am I overfitting? If I am, I should be regularizing. Okay, so these are all the different things that you need to think about. And obviously there's a lot to think about, right? But this is just to touch on some of them and give you an idea of what are some of the things to look at. All right. And so from there, you would say this is one particular type of architecture of deep net. From there, you might say, okay, well, that's bad because our unrolling an image wasn't great because you're looking at the whole image at once. It's this global thing. For images, you maybe got these more specific visual local things, right? For an 8, we want to represent a loop there and a loop there. And so if we can build a network that represents that and only looks in local areas, that's better. And so you get things called convolutional neural networks, where you can learn more local features within your data. And then the convolution moves around on your input. So on an image, it moves around in the image. Through time, it can move through time. And then it will tell you if it detects something at different positions. And then based on that, you can have fully connected layers later on that will give you a sense of 2 loops in these positions tells you it's an 8, right? And so convolutional neural nets do that, taking into account this local information, and I think we can probably leave it at that point. Okay, so thank you very much for listening. I definitely suggest reading up a little bit on convolutional nets, but that's probably a full lecture in itself as well. Okay, but I hope that gives you a sense of what are these deep neural networks, how do we train them, what do we mean when we say it's deep, and what are we hopefully learning within these deeper architectures. All right, thank you very much.
Richard, thank you very much for that. I know your best summary that you could give on deep learning and all the neural nets. So just to sort of like clarify a bit of my understanding. So in terms of deep learning, is it exclusively neural network based, or are there any other approaches to achieving deep learning as opposed to going the neural network?
There certainly are different approaches, and you can look at things like different types of Boltzmann machines, restricted Boltzmann machines, and things like that, which can also have these layered approaches. You don't only have these neural approaches to it, but certainly neural networks are by far the most common, and it's the one that you're most likely to see, and certainly the ones that are solving all the problems at the moment.
Okay, thank you for that deep lecture, which got me confused a bit. You started off with X, and then you had the weights, and then that thing you called, and then you had binary 0, 1. But now when you went to, what did you call it? The layers of neurons. Now you're on the graph that which was sort of like centered at 0. Now it was a sigmoid. And now the y-axis was no longer 0 and 1, but it was more between taking other values, not necessarily 0 and 1. So how did you convert that 0 to 1 into something which was more like a sigmoid, meaning that it was taking other values?
And so the idea generally is that you'll pick some threshold and say if sigmoid is giving you a value above something in the middle, then it's going to be a 1, and if it's below that, it's a 0. The idea of using the sigmoid itself is that it's continuous and differentiable, right? So it gives us nice gradients, so we know steps to take in between, as opposed to just having a step function, right? And so we use the sigmoid because it gives us a gradient, or ReLU, or any of those because they give us gradients. But at the end of the day, if we want a classification, right, we want to say it's in the class or not. And so you would then have some kind of threshold where you say if it's above the threshold, it's in the class. If it's below the threshold, it's not. The sensible threshold to pick is 0.5, but you could do something more interesting with receiver operating curves and kind of precision and recall things to pick a smart threshold.
My question is specific now, how do you move from, what did you use actually to move from that 0 to 1 to those values in between?
Oh, just the sigmoid function. Yeah, just the sigmoid, yeah.
And now we have two variables, x1 and x2, but your sigmoid function 1 over 1 plus e to the x, was the x a vector?
Yeah, it's a vector. It's a vector, so it's just the dot. So in the sigmoid, we've got e to the power of something dot x. So it's just a dot product in the power of the exponential. And so if x is a vector of length 50, you have 50 weights plus a bias. And you just do the dot product there, that gives you a scalar number, and then sigmoid gives you a scalar number.
Do you choose the batches of data? How do you know, instead of just all of those big data, how do you choose it? And how many batches do you need to choose?
It all kind of varies. I would say that it's based on your computational restrictions, right? So if you have, often what we do is we'll take a neural network like this, and we'll say we can evaluate 10 things at the same time by putting them on a graphics card and getting the graphics card to do the matrix multiplication in parallel, which graphics cards are very, very good at. That's why we use them for deep learning. And so you can generally take a batch, put it on a graphics card, and then do the forward propagation in one step, as opposed to once for everything in the batch, right? And so I would say your batch size you want to be as big as possible while still fitting in memory on the graphics card that you're going to be using. So if you've got 12 gigs of RAM on your graphics card, then you want your batch size to probably be as big as it can be without overflowing those 12 gigs, right? Then you would also want to make sure that during training, you cover your entire training set, right? So you probably wouldn't want to take some samples in your training set, train on them, and then train on them again and again without having visited the rest of your training data, right? So in general, what you would do is probably just take a random subset, and that's fine. But you do want to make sure that you train on all of your training data as well. So you don't just want to take the same random subset. You want to train on that random one and then say train on a different random one and a different random one until you visited everything, and we would call that an epoch. Right? So once you've visited everything in your training set, you've had one epoch, and then you have a second epoch and a third epoch and a fourth epoch, and you keep revisiting everything until you see that you're starting to overfit, or if your network diverges, or if it's converged to something sensible, then you can stop as well.
Hi, I just would like to understand, how do you upfront choose the number of neurons and layers? There must be some sort of a trade-off.
That is a very good question. And we don't really have particularly good answers for that at the moment, I'm afraid. A lot of, what's very interesting is there are a lot of these kind of big networks that everyone knows. So there's AlexNet and VGG and Inception and these specific architectures that just seem to work, right? And so my general advice would be that often if you have a very big problem, one of these architectures is a good one to use because we know these architectures work well. The kind of theory of how do you design your network is quite hard. A lot of people use reinforcement learning to do it. Maybe it's premature to talk about that because there's a reinforcement learning thing coming up. But the idea of reinforcement learning is to say it's like learning to walk. Right? You get a signal when you've done it right and a signal when you've done it wrong, but it doesn't tell you whether how to do it. Right? So if you're learning to walk and you fall over, you get a negative reward because it hurts. If you're learning to walk and you take a step and everyone around you is happy because you're a baby and you're now learning to walk, you get a hit of dopamine and that's a positive reward, right? But no one's told you this is how you walk, right? And so so reinforcement learning is a very natural way of approaching this idea of add neurons, add layers, remove neurons, and explore the space of the different architectures. But in general, it's a difficult problem and it's an open problem that people are still working on.
I was saying my question is about how important cross-validation is as part of...
And I would say in general, it's quite important because in a sense, you are, at the very least, when you take your training data, you probably actually want to split it into more than just your training and your validation, your training and testing. You want to split it into a validation set as well, right? So you've got your training set. So you have a model, you train it on the training model. Then we test it on the validation set, right? And then we train a different model and we test it on the validation set. And we train a different model and we test it on the validation set. Right? Then, of all of those models, we pick the one with the best validation score. But we've now learned something from the validation set, right? So we can't test again on that, right? And that's when we pull out this extra test set and we would test on that. I would say at the very, very least, you need to be splitting into those three sets, okay? Cross-validation is nice because it allows you to explore the space without saying, well, what if I got a bad validation set? You know? Because you can kind of say, well, take your entire set, split it into these 5 or 10 or 20 or however many folds you want in your validation set, and then train on this combination and test and validate on the other, and then rotate through and try all the different combinations. The downside of that is it takes forever, right? Because now if you want to say we've broken into 10 sections, and we've got training on 9 and let's say testing on 1, Then we train on the other 9 and test on 1, and then train on the other 9 and test on 1, and the other, right? So we've now had to train 10 times, right? If it takes a week to train your neural network, that's a long time to test, right? So, there's a trade-off. Like the more cross-fold validation you can do, probably the better faith you can have that your model hasn't overfit, and the better sense you'll get of how well it will generalize to other data, right? But it is a trade-off in how long it takes to actually train the network and run it.
You talked about feature learning and sort of that the net learns representations and features and that are successively more abstract until it gets to sort of a final answer. 2 questions. How do we know that neural nets actually do that rather than just something that we think they do? And also, how does backpropagation sort of cause that features to be learnt by the net?
And what's interesting is that the answer is it's contested. People contest that that's not what it does. And so there is open research about that happening. There are a lot of people who are saying maybe that isn't the same thing. And in fact, one of the research talks that happened in the other track in the previous session was on the idea that random weights actually do quite well, right? And so you can have a network with random weights and you can only learn the end layer, and you're still, like, it's not as good as backprop, but you do quite well, surprisingly well, right? And so the real point is that this is what we think it does, and we're still working more than that. If we do go into something like convolutional nets, so convolutions are, you almost have a little, this little filter, and you move the filter around an image, and it will respond in certain ways. And with specific filters, we can see what it responds to, right? And what's interesting is that in convolutional neural nets, they learn things that are very similar to something called a Garber filter. And Garber filters generally pull out orientation and scale type responses for edges. And it's interesting because they're very similar cells in our visual system that responds in the same way. And so within convolutional nets, we can actually see it happening, certainly with the convolutions. But this idea of the fully connected nets, it's very difficult to tell. Some ways that you can also look is really to show it lots of images and try and see which images excite a specific neuron, right? And you can do those kind of tests, but overall it's a very hard problem, and it's one that people are still looking at. Yeah. So this is just the current working theory that people tend to have.